Refer your clock's tables for tan 35. So this turns out to be 7. Just knowing basic concepts, basic relations, we are able to calculate things very easily. So for every series, the value of N1 is fixed. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram, Pre-University, Mysuru. A new session. I will be continuing the discussion on numericals from the model question papers. The first problem. The problem says the electrostatic force on a metal sphere of charge 0.4 microcoulomb due to another identical metal sphere of charge minus 0.8 microcoulomb in air is 0.2 Newton. So the electrostatic force acting on a charge 0.4 microcoulomb due to another charge 0.8 microcoulomb is 0.2 Newton. Find the distance between the two spheres. Distance between the two spheres and also the force between the same two spheres when they are brought into contact and then replaced in their initial position, and also force between same two spheres when they are brought into contact and then replaced in their initial positions. Now let us take down the data. The magnitude of the first charge is 0.4 into 10 power minus 6 coulomb, and the magnitude of the second charge Q2 is minus 8 into 10 power minus 6 coulomb. Given so, the electrostatic force between them is 0.2 Newton. So F is equal to 0.2 Newton. First, I will calculate the distance between the two spheres. Dear students, having this data, how will I find the distance between the spheres? Mr. Coulomb is there for our help. So, F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. R is the distance which has to be evaluated. So F is 0.29 into 10 power 9. Q1 according to the data is 0.4 into 10 power minus 6. Q2 is minus 0.8. But as I say always, to calculate force, don't use the negative sign on the charge. Negative force is only repulsion. So this is 0.8 into 10 power minus 6 divided by R square. So on simplification, R turns out to be 0.12 meter. So the simplification is left for y'all. These are simple simplifications. Your ordinary calculators can do this. Now, the next part of the problem is interesting. Now I have to calculate the force between the same two spheres when they are brought into contact and then replaced in their initial positions. The two spheres are brought into contact. When the two spheres are brought into contact, Q is always Q1 plus Q2 divided by 2. So when the two spheres are in contact, the charge on them is Q1 plus Q2 divided by 2, which is 0.4 minus 0.8 divided by 2, which is equal to 0.2 microcoulomb. Now distance is known. Q1 and Q2 is known. The new force I call F dash 1 by 4 pi epsilon naught Q1 Q2 by R square. Or this is 9 into 10 power 9. Q1 is 0.2 into 10 power minus 6. 0.2 into 10 power minus 6 by R square whole square, which is equal to 0.025 Newton. So very easily again I have simplified the problem. Next one, students. A resistor, an inductor, and a capacitor are connected in series with 120 volts, 100 hertz AC source. So a resistor, an inductor, and a capacitor are connected in series with 120 volt, 100 hertz AC source. voltage leads current by 35 degrees. If the resistance of the resistor is 10 ohms, the resistance of the resistor is 10 ohms, and the sum of inductive and capacitive reactance is 17 ohms. Calculate the self-inductance of the inductor. Now, to begin with, he says, VRMS is 120 volts and the applied frequency is 100 hertz. Very clearly, current is leading voltage by 35 degrees. So phase difference between current and voltage is 35 degrees. And the sum of inductive and capacitive reactance is 17 ohms. Sum of inductive and capacitive reactance, XL plus XC is 17. With this, students, I have to calculate the self-inductance L of the inductor. To begin with, I know the expression for phase difference where we write tan phi is XL minus XC by R. Now, if I calculate XL minus XC, I get two simultaneous equations. So, XL minus XC is tan phi into R. Or XL minus XC is tan 35 degrees into 10. So XL minus XC, refer your Clark's tables for tan 35. So this turns out to be 7. So I have got the value of XL minus XC. Now, it is given that XL plus XC is 17. I know XL minus XC is 10. So here, on simplification, XC cancels. 2XL is, when we add up, so this is 7. So 24, or XL is 12 ohms. So from this XL, can I calculate self-inductance L? Yes, XL is nothing but 2 pi FL, which is 12. Substitute 2 into 3.14 into 100 into L is 12, or on simplification, L turns out to be 19 millihenries. So 19 millihenry will be the answer. The next one, students. Again, an interesting problem. A beam of light consisting of two wavelengths, 500 nanometer and 400 nanometer, is used to obtain interference fringes in Young's double slit experiment. The distance between the slits is 0.3 millimeter, and the distance between the slits and the screen is 1.5 meter. So the distance between the slits is 0.3 millimeter, and the distance between the slit and the screen is 1.5 meter. Compute the least distance of the point from the central maximum where the bright fringes, very clearly, bright fringes due to both wavelengths coincide. So very clearly, he is saying this is a case of bright fringes getting formed. So we have x1 is equal to x2. Now, what is the distance of a bright fringe from the central maxima? N lambda d divided by small d. Now, this is n1, lambda 1. So, this should be equal to n2 lambda 2d divided by small d. So, when we equate n1 by n2 is lambda 2 by lambda 1. So, lambda 2 is 400 nanometer. 400 into 10 power minus 9. 500 into 10 power minus 9. So, this gets cancelled. So, very clearly, n1 is 4, n2 is 5. Now, what is that I have to calculate? As given, distance of the bright fringe from the central maxima. Again, x is n lambda d by small d. So, how much is n corresponding? 4 into 500 into 10 power minus 9. Now, the distance between the slit and the screen is 1.5 divided by the distance between the slits, 0.3 millimeter. So, 0.3 into 10 power minus 3, which is 0.01 meter. Just knowing basic concepts, basic relations, we are able to calculate things very easily. The next question from atoms. First member of Balmer series has a wavelength of 656.3 nanometer. Calculate the wavelength and frequency of the second member of the same series, which is Balmer series. So the wavelength of first member of Balmer series is given. So for first member of Balmer series, so for every series, the value of N1 is fixed. So this is N1 is 2 and N2 is 3. Now we know 1 by lambda is R, 1 by N1 square minus 1 by N2 square. Or here it is given to be 656.3 nanometer into 10 power minus 9. So this is 1 by 4 minus 1 by 9. So on simplification, so this is equation 1. I have to find the wavelength and frequency of second member of the same series. So for second member of Balmer series, second member, N1 is 2 and N2 is 4. The same way now, this is 1 by lambda is R, 1 by 2 square 4, 1 by 16, I call this equation 2. So equation 1 divided by equation 2. So lambda is 486 nanometer. So the wavelength of the second member of Balmer series is 486 nanometer. Now with this, I will also have to find the frequency. How will I find the frequency? See, we know nu is, C is nu lambda 2, or nu is C by lambda 2 equate so many hertz will be the answer. So again, students, quite effectively, I have worked out problems from the model question paper. Practice these problems, become thorough. Have a nice time. Thank you.